Hello, in this video we will look at a theorem and 4 example questions. Now we will not prove the theorem in this video, so I'm just going to state it here and we'll talk about the proof and reasoning behind it in a separate video. So the theorem says, let V be a vector space of dimension n. If S is a set containing V1, V2, all the way up through V sub n, so if S is a set of n linearly independent vectors in V, then S is a basis for V. And the second part of the theorem says that if S is a set of n vectors that span V, then S is a basis for V. So let's look at 4 examples. These are true-false questions. The first one says every set of 3 linearly independent vectors in R3 is a basis for R3. Well, that actually matches part 1 of our theorem. If we look at part 1 of our theorem, we say that if we have a set of, for example, 3 linearly independent vectors in R3, then we have a basis for R3. So this actually turns out to be true by part 1 of our theorem. Number 2. There exists a set of 4 linearly independent vectors in R4 that is not a basis for R4. Well, that's false. Again, by our theorem, part 1, we know that if we have 4 linearly independent vectors in R4, then we do have a basis for R4. Part 3. There exists a set of 2 linearly independent vectors in R3 that's not a basis for R3. And you know, we could think of an example that satisfies that. For example, if we had a set of vectors that look like 1, 0, 0, so that's the famous I hat vector, and then we have a 0, 1, 0. That is certainly a set that is linearly independent, but it does not span R3 because, you know, there's nothing in that third component. There's no way we're going to get any vectors that live outside of the xy plane. So let's go back to our question. There exists a set of 2 linearly independent vectors in R3 that is not a basis for R3. That's true, and there's the example. Number 4. There exists a set of vectors in R3 that spans R3, but which is not a basis for R3. That turns out to be true. And you might be wondering, well, wait a minute, I thought part 2 of the theorem, guarded against that. Well, what part 2 of the theorem says is that we had n vectors that spanned an n-dimensional space, right? And then in that case, we certainly do have a basis. But down here, they didn't tell us how many vectors we have. And so we could think about a set, let's say we've got I hat, which is 1, 0, 0, j hat, which is 0, 1, 0, and k hat, unit vector pointing in the z direction. And so those are linearly independent, and they certainly are a basis, but let's throw in one more vector here, like the vector 1, 2, 3. Well, this set certainly does span, so that set spans R3, but it's not linearly independent. So this, let's say, is linearly dependent. And since it's linearly dependent, it's not a basis.